So I will talk in English because if I have to choose between my broken English and my broken French, maybe better. I don't know what. Let's talk in English. And so it's a privilege to contribute to this conference. And I'm very happy to be here to celebrate this anniversary of the IPhT. Therefore, I'm very grateful to the organizer to having thought at me for this talk. And as you are here for the IPhT, I also wanted to thank Katrina, that I don't see now, but for the work she puts in the Institute and for her supportive behavior. And so I'm going to tell you some research that I did more or less at the time when I joined the IPhT, which has to do with the Eigenstate thermalisation hypothesis that I will tell you what it is about, but is a point of view of on the many-body problem and somehow from a statistical mechanics perspective. And the nice thing it is that it has some tight connection, at least in the way in which I see it, with random matrices. And and this is, as Pier Francesco called it, the temple of random matrices. And because the field of random matrices and free probability, which is something I will mention at the end, has been revolutionized by the progress made in this lab. So my talk will be kind of not very broad, and I won't give an overview of this famous paper that proved to be so important for this field, not because I don't recognize their importance, but just because somehow I don't feel the qualified person to do it. But still, they are very important, and they prove to be important also for my personal research and for the fields that I'm going to discuss. And okay, so I will try to be short, as my talk is towards the end before the celebration, final celebration. And let me start. So the reason why what I'm going to tell you has been proposed in the literature was the need to give a mechanism, an explanation, a mechanism which could explain the way quantum isolated system with a large number of degrees of freedom thermalize, in the sense that they are described by their asymptotic properties. They are described by quantum statistical mechanics. We ended up to do this project, not because we wanted to study thermalization, even if I'm very interested in this type of topic, but just because we wanted to rephrase some problem at equilibrium within the scheme provided by the Eigenstate thermalization hypothesis. And we understood that there were some ingredients which were missing in this formalism, and that we try to incorporate and to complete in some way. So my talk will be about, despite its name, about dynamics in equilibrium. And so the most naive thing that you can think of to write down the dynamics of a quantum system for your first course of quantum mechanics is to think to it in the Heisenberg picture. And this is because in the end, the Eigenstate thermalization hypothesis is focused on some observable more than on the wave function, even it is fundamental to understand the properties of the eigenvectors. And if you write it like this, you understand that the key ingredient that you have to understand and characterize are these matrix elements in the basis of the energy eigenvectors. And however, there is a lot of redundancy. So if you think to a many-body problem, you have your Hilbert space, you have an immense number of matrix elements, and you better think to them in some statistical way, some very generic and statistical way, if you want to characterize them instead of giving one by one or their value. And a way in which I like to introduce the ETH, as sometimes it is difficult to digest if you are not familiar with it, is starting from this example, which is borrowed indeed from random matrices, which gives an example of a toy ETH in which my Hamiltonian is given by a GOE, for instance, a random matrix. Then I know that its eigenvectors are given by a random unitary orthogonal, it's the same matrix. And then the question that I ask is, how do matrix element of my observable, which for simplicity I take diagonal, but could be not, look like in the basis of the eigenvector, which is this random unitary. So the first thing I can compute is the average of a diagonal matrix element, and this turns out to be equal to the first moment of your matrix. That later will be clear why I call it K1. K1 is the first free cumulant. So these diagonal matrix elements are fluctuating, in general random, but they have an average which is of order 1 in the size of the space of the matrix, in the size of the matrix, which is this n here. And the fluctuation I don't discuss in this slide, but turns out to be polynomially suppressed in the size of the system. Now, if I look at off-diagonal matrix elements, these off-diagonal matrix elements are on average 0. This is normal because there is no content in the phase of the eigenvector. So, and however, they are still there. Indeed, if you want to compute a second moment, we need off-diagonal matrix element. And these off-diagonal matrix elements have a variance. Sorry, I'm a bit, I don't know what this is. This is better. And their variance is suppressed by a power 1 of the size of the system. And it's, the prefactor is proportional to this second moment minus the square of the first moment, which looks like a variance, and I call K2. And and then I immediately can write down what is the analogy of what you will see will be the toy analog of what will be the ETH for a quantum system, which is just the properties about this matrix element. What I told you is that you have a diagonal matrix element, which is an average, which is order 1, and then very small of diagonal matrix elements. This Rij, a random number that I don't tell you anything, even if I suppose I could tell you that are Gaussian. And their average is equal to 0, and their variance is equal to 1. This is okay, it's good. These are modeling the properties of this matrix element, but it doesn't say anything about the joint probability of this matrix element. And indeed, if I look at correlation between matrix element, if I take products of indices which are concatenate but do not repeat, you can show that this value, this average, is suppressed, is very small, and as soon as you increase the number of this product, number of terms in this product, is suppressed by n to the power p minus 1. And then the prefactor is this famous free cumulant. So to make connection with the history of IPhT, let me just say that a way that I know to show this result is the famous integral formula of Jean Bernard and Itzitson in the limit of osmol rank. Let me just comment about this free cumulant that I will come back to this at the end of my talk when I will talk about just mentioned free probability. These are numbers that probably you know better than me, but are, so let's say that are well-defined quantity in terms of the moment, which describe connected correlation for random matrices. And so I like this way to represent this. So I'm not saying what is the distribution of this matrix element, but I'm saying what are their correlation which characterize this distribution. And it turns out that the building block are these products of loops that I like to characterize in this way. This is a diagonal matrix element of index II, which so an edge is a matrix element and the vertex is the index. And then this is a diagonal matrix element. This is the variance of an off-diagonal. And this is a 4-point term. And OK, so this is about the ETH. And basically what we did was, so this, the ETH as it was written for the many-body problem is a sort of generalization to this. To these ansatz of matrix element in the basis of the eigenvector of the Hamiltonian for a realistic system. And what he did was the essential was to take into account the fact that the bottom line is that we took into account the fact that there were higher order correlation to be included. So why I want to, or better than me, people before me who, like Zrenitsky and so on, that wrote down these ansatz, wanted to pursue this way of thinking of random matrix element, because if you want, so ETH was born in the field of quantum chaos of the 90s, and that also was the focus of some research in this lab. And people like Barry were suggesting that we can think to the eigenfunction of chaotic system as random waves. So this way of thinking that there is some randomness, even if it is difficult to characterize, difficult to access, but it should be there in your problem, led these people think that it was a good way of thinking to this matrix element as random numbers. And so the typical setup is that of a system on a lattice. You can think to your observable as this, or also the local one. Actually, now I realize that maybe it's better if I should put the local one. And now, what was the size of the matrix is parameterized by big N, which is the number of particles, which is the parameter that I tune. Usually in a system, I don't tune the size of the system, but I tune the number of particles. And this space is huge. And what is important is that, so I can think effectively to have different, that at each energy shell, at each energy density, have an effective exponentially large Hilbert space with a size which scales the density of states. And the bottom line of the ETH and the way in which you explain the thermalization is the idea that if you look to the diagonal matrix element in your problem, if you look at the nearby energy states, they don't fluctuate too much. They are more or less the same if you look at the same energy density. So, and in some way, the name means the fact that each eigenstate provides a realization of a microcanonical ensemble for the quantum problem. You don't need to sum over a window of microstates. You need one. And however, so Zrenitsky was interesting also to write a generic ansatz also for the off-diagonal matrix element, because if you want to understand the dynamics clearly, you cannot forget about the off-diagonal matrix element, otherwise there is no time dynamics. And this is how the ansatz is usually written. So I forgot to underline that in the TOI-TH, the numbers that are in the diagonal and in the off-diagonal are completely independent on the index, because there is a permutational invariance between the eigenstate. One is like another. While in a quantum system, it's reasonable to think that you have this permutational symmetry between one eigenstate and another, because at high energy, for sure, you don't expect the same properties at lower energy. And therefore, this generalization must carry some information about the energy that the matrix element refers to. And the way in which it is written is it means that so the diagonal matrix element have this is a function A of the energy, basically the energy density that does not fluctuate, is a well-behaving function of the energy density. And then the off-diagonal matrix elements are here are exponentially suppressed, but remember that the analogy between the size of the space and the number of particles is exponential, so it's just equivalent to a polynomial suppression in the size of the effective Hilbert space at that energy. And on top of this, what was before K2, what I call K2, the variance of the matrix, has to be taken into account as a function which depends on the energy density, but also on what I call a frequency. Maybe it will be clear in the next slide what I call frequency, because it is an energy difference between the two energy associated to the index of diagonal matrix element. And this is a true realization of one of these Hamiltonian. And when you see that, so when you move along the diagonal, you are basically changing the average energy. And when you move away from the diagonal, you change omega, this frequency. And you clearly see that this function has a structure which decays away from the diagonal. And it is important for the dynamics. I come back to a point which maybe I already alluded, that is difficult to, so I'm talking about here random matrix element, but the problem is not well defined because I don't have an ensemble to define, and the way in which we think to this, so people do numerics, compute also statistics of this matrix element by taking samples in the same energy windows, because you think that statistically there is not much difference between nearby matrix elements in closed windows. And more theoretically, we think to this ensemble as ensemble of Hamiltonian, which is slightly perturbed one to the other, but that this perturbation is tiny and descends to zero in the limit of the thermodynamic limit, so that no physics should be affected in the end by this perturbation. And so one can do there is a way to do calculation with this type of ansatz. And what you find out is that if you compute an expectation value at a certain for one point function, a certain temperature, you in the thermodynamic limit, you recognize that it is equal to the value taken by those diagonal matrix element at the energy conjugated to the temperature. And if you take this connected function, you realize that it is equal to the Fourier transform of this function f of omega, which was defining the prefactor in the off-diagonal matrix element. But if you write down one-point function and two-point function in the Heisenberg representation I was showing at the beginning, you immediately realize the striking factor that they don't depend of the correlation, so they don't contain products of different matrix elements. While if you go beyond two-point function, you will encounter product of different matrix elements, which is peculiar at the level of pre and four, of three-point function and on. So why we ended up to think to this problem? Because we wanted to apply ETH to study the out-of-time order correlator, which have been discussed in the field of this new wave of quantum chaos recently. And so we wanted to study four-point function, and immediately, as I was saying, you realize that you have to take into account, say something about the product of different matrix elements, which was not present. So in the answer. So I don't know if people thought before that they were independent or they didn't have just an opinion on this. But taking them as independent, which is maybe the ansatz number 0, would lead to a hyper-universal formula of the endpoint correlation function in terms of two-point correlation function, which is not expected to exist, seems too general to be true. And then we started to think what would be the natural correlation to take into account. And for sure, this correlation shouldn't depend on the phase of the eigenvector. So only indices which are concatenate should appear. And at least I was very much motivated by this toy example of toy ETH, to think that the natural generalization of ETH at the level of higher order correlation functions should be to take into account this type of diagram, which are product of indices which are concatenated but do not repeat. And this hopefully would be the building block of this correlation function. And in particular, so it should be, if you look for instance, an out-of-term order correlation function, and so you want to look for some new physics which is encoded in the 4-point function rather than in the 2-point function, you better look to this type of correlation than to the variance of diagonal matrix element. And indeed, all this is very natural because, as I said, this ETH contains already these two types of diagram in my representation. You just need to just generalize it. And so what we wrote was this ansatz. Well, this factor here is is meaning that, so it's an exponential factor which is suppressing the number of products that you have. So it means that these matrix elements are also uncorrelated. Correlations are very small. But in the end, when you use it to compute a correlation function, you'll be better care of this because at each index, you sum and you gain an entropic factor. And so this small correlation in the end matters. And so all this was the beginning of the story, and then a sequel was that. So we in the end we made a bridge with this free cumulant and free probability that I was talking about. So you probably know, as I said, better than me what is free probability, but just to be on the same foot, let me say that is a field which deals with non-commuting random variable. It has received a growing interest since when its relation with random matrices has been established. But as we are here, I also wanted to say that I think that the seed of random probability in connection with random matrices was already developed here at IPhT in the famous paper of Jean-Bernard Edouard. Well, at least there was the generating function of the free cumulants. No, this is fair to say. No, but there was the free, okay, I wanted to say that there was this generating function of the free cumulants. And so yeah, to go to my talk is so we established, so before I was saying that for ETH, each product of a matrix element is a prefactor which is equal to this free cumulant. And now for the, which is suppressing the size of the system, but then for this many-body problem, if you sum over all the indices, being careful to not repeat the indices, you can identify, so basically the rule that we give for ETH, maybe it's not too surprising because it's inspired by this toy example of ETH, but you recognize in the expression of the correlation function the moment cumulant formula that allows you to define the free cumulant in terms of this sum of products. And these products in the end are related to this function present in this ETH that we have discussed. And okay, that's it. So I'm still don't know all this bring, but maybe there is some hope that it will be interesting to deepen the understanding in this direction. And so I just wanted, so what we did was to propose a simple ansatz to take into account this correlation of matrix element, and we wanted to make a connection to advertise this relation with free probability, which I don't know if Michel also has worked on this with Denis and collaborators. And with this, I thank you very much, and I want to say happy birthday to you.
Thank you, Laura. Questions?
That's a stupid question. How does, when you have this time correlation function, how do they behave with time? I mean.
No, so it's very general. It is expected to describe at high temperature. So.
No exponent. No.
Yeah. Typically, you expect an exponential decay at high temperature. Yes. but it's kind of general. So you don't know whether, so if you give me a Hamiltonian, I'm not 100% sure that all this machinery works, but there are some type of model where people have checked that this type of prediction works.
Recently, people start discussing correlation function conformal field theory in the limit when some operators become infinitely heavy. Like think like 4-point correlation function when two operator becomes infinitely heavy. And there's some speculations about the behavior of those correlation functions in this particular limit. And I heard the statement about exactly this ETH conjunction being verified in that case. Could you comment on the relation between these two
Yeah,
things?
so I know that there have been development in the more field theory community. So I'm less on the so for instance, I know that there have been also results discussing the probability, the ensemble of this matrix element, which is able to reproduce this thing. Then I don't know, because I'm not so specialized in this classification of operator, but I would be happy if you.
But could you just, for non-expert, could you give just physical interpretation why it should be, to start with, what should be any relation between completely different things? Because the way how you present is just properties of the eigenvalues of the random matrices. But why should the same DTH conjecture should be applicable to situation when a priori it has nothing to do with what you were talking about?
I don't know if I heard that. You want to say why I jumped from random matrices?
No. I just, for non specialist, what should be kind of the physical reason why this ETH should be applicable to object which I just mentioned, given the fact that it seems like no really direct relationship to the random matrices?
So I think that all the field of quantum chaos and so on is somehow related to the field of random matrices. I don't know if it is clear. I think it is not really clear why it works so well. So the idea that you had in mind, but I didn't insist on this because it's far from being mathematically rigorous, is that you have a sort of local invariance very close to the, instead of having a full invariance over a random unitary, let's say you have a local unitary which looks like a random unitary close to the diagonal, but then it decays. This is because if your ensemble is given by different Hamiltonians which differ little one from another, so eigenvector will be very sensitive nearby eigenvector by perturbation. But then if you take far away eigenvector will be insensitive to this perturbation. So we expect this local invariance, but as I said, is not is more an ideal.
Other questions?
If you have time, otherwise. Can we return to your slide number 9, please?
9?
9, yes, halfway. Yeah, no, maybe the one before, the one with the exponential of, yes. I think it was another one. Anyway, okay, maybe.
The TOEIC or the
I was curious to know whether it was an ansatz or a result that you had established. There was an exponential of S of, that was this distribution along a sort of domain along the entire diagonal.
This is a true realization of Hamiltonian.
Yes, that one. That's indeed 9, number 1. Okay, so yeah, in the upper formula, this S of E, is it an ansatz or is it something that you can determine?
No, it's basically an entropic factor that you need to put if you want in the end, when you will sum, like you compute a 2-point function, you will sum over the indices, you will gain a density of state for each index that you sum. And so you need exactly that factor in order to make your quantity for order 1. Okay. But this is exactly the analog of this 1 over n that you have here. this exponential,
Mm.
because the size of the Hilbert space is exponential in n.
Okay.
So this is exactly this factor here.
Okay.
It's exactly the same thing. Just it depends on the n, on the density of state. It's not like.
Okay, Pier Francesco, last one and short, please.
Yeah, so I wanted just to ask maybe a vague question about this comment that you made on the ensemble that is ill-defined, but you, in some way, you try to define it by some stochastic stability, in the sense that you put some random perturbation, and this random perturbation is sufficiently small, so I guess that epsilon scale like n to some power.
Yes.
And I mean, is just an idea, or it has been done something?
No, we at least, I mean, I think it's not even our idea, it's, I think, but yeah, I was studying Deutsch for it. But no, I don't know if something really mathematical can be done to do
Okay.
it.
Thank you.
Okay, let's thank Laura again.